all been told that planting trees is a good answer to climate change. And while trees are amazing, they only grow so fast. But what if we could build mechanical trees that work thousands of times faster? Today we're looking at the world of carbon capture, from giant fans pulling carbon dioxide out of the sky, to turning gas into solid stone, to storing it underground. We are witnessing the birth of new industry. But as we'll see, technology isn't a get-out-of-jail-free card. It's a tool that only works if we use it correctly. Welcome to the podcast. I'm Dr. Mack, and this is the Climate Translation. Our first stop is direct air capture, or DAC. Imagine a giant wall of fans pulling in the same air you're breathing right now. Inside these machines are chemical filters. You can think of them like sponges, designed to grab onto carbon dioxide molecules while letting everything else pass through. Nitrogen goes through. Oxygen goes through. Carbon dioxide gets caught. Once those filters are full, the machine uses heat or pressure to squeeze the carbon dioxide back out, and what you're left with is a concentrated stream of carbon dioxide, no longer spread thinly through the atmosphere, but collected in one place where it can be stored or used for industrial purposes. At a basic level, the idea is that simple, and it works. Right now, the world's largest direct air capture facility removes on the order of a few thousand tons of carbon dioxide per year. That's impressive engineering. But it also highlights a challenge, because humanity emits around 36 billion tons of carbon dioxide every year. So even the biggest DAC plant operating today is a very small piece of the puzzle. It exists because carbon dioxide mixes evenly through the atmosphere. Once it's released, it doesn't stay near the source. It spreads everywhere. Direct air capture takes advantage of that fact. It doesn't make a difference where the carbon came from, a car, a plane, a power plant. DAC can pull it out of the air anywhere. That flexibility is a great strength, but it's also the reason DAC is hard. Carbon dioxide makes up only about 0.04% of the air. Pulling it out means moving enormous volumes of air. Moving air takes energy. Heating filters takes energy. Compressing and storing the gas takes energy. This is where most of the criticism of direct air capture comes from, and fairly so. If a DAC system is powered by fossil fuels, it can end up removing far less carbon than it emits. In worst cases, it becomes an expensive way of just moving carbon around without actually helping at all. That's why recent breakthroughs matter. In 2025, researchers developed new materials and processes that cut the energy required for direct air capture roughly in half compared to older systems. Now, that doesn't magically solve the scale problem, but it does move DAC from a laboratory curiosity towards something that could realistically work alongside things like renewable energy. Even so, the scale remains a hard limit. To make meaningful impacts, direct air capture would require thousands, possibly tens of thousands, of large machines running continuously, powered cleanly, and connected to places where carbon could be stored safely for millennia. Now, that's not impossible, but it's not fast, and it's definitely not cheap. So the right way to think about direct air capture is not as a silver bullet, it's more like a cleanup tool, especially useful for emissions that are hard to eliminate, like aviation or shipping, or for removing carbon that's already in the atmosphere. And that leads naturally to the next question. If pulling carbon directly out of the air is this difficult, what happens when we try to capture it before it ever spreads to the atmosphere? Geological sequestration involves taking carbon dioxide gas, compressing it until it behaves like a dense, liquid-like fluid, and pumping it thousands of feet underground into specific rock formations. And no, we're not dumping it into giant underground caves. Instead, we're injecting the carbon dioxide into tiny spaces within rock, the microscopic pores that once held oil, natural gas, or deep salt water. Think less empty cavern and more sponge made of stone. The most important requirement is something geologists call integrity. That means the storage layer has to be capped by thick, solid rock that fluids can't pass through. The rock acts like a lid on the jar, keeping whatever's underneath from slowly leaking back out. As long as the lid stays intact, the carbon dioxide remains trapped. If the idea sounds familiar, it should. It's exactly how oil and natural gas stayed underground for millions of years. The Earth already has a proven track record of storing fluids safely at depth, long before humans ever drilled a well. In that sense, geological carbon storage isn't inventing a new system, it's using an old one in reverse. We're taking carbon that was locked underground for geologic time and putting it back into similar formations, essentially returning it to Earth's long-term savings account. Of course, at this point, my students often ask me, what if the carbon leaks? What about earthquakes? Aren't we just delaying the problem instead of solving it? And they're fair concerns. The reality is that underground storage is not risk-free, but neither is leaving carbon dioxide in the atmosphere. The difference is that underground risks are local and monitorable, while atmospheric carbon affects the whole planet. Modern storage sites are carefully chosen, mapped, and monitored. Scientists track pressure, chemistry, and movement over time. If carbon starts migrating where it shouldn't, operators can detect it early and respond. That level of control simply doesn't exist once carbon is released into the air. But geological sequestration does have limits. Storage sites are not evenly distributed across the globe. Transporting carbon dioxide requires pipelines or shipping infrastructure, and while underground storage can handle large volumes, it's not infinite. More importantly, the approach doesn't make the carbon disappear. The carbon is still carbon dioxide. It's just relocated, liquefied, and trapped physically instead of chemically transformed. And that distinction matters because it sets up an important contrast. Geological storage relies on containment. It works as long as that rock lid holds. But there's another approach that doesn't rely on lids at all. Instead of trapping carbon dioxide as a fluid underground, it changes the carbon itself, turning it into solid rock that can't leak, migrate, or escape. It's called mineralization. Instead of relying on pressure and containment, mineralization changes the carbon itself. In certain types of rock, especially basalt and minerals like olivine, carbon dioxide reacts chemically with the rock. When carbon dioxide comes in contact with these minerals, it doesn't just get trapped, it gets transformed. The carbon bonds with calcium, magnesium, or iron in the rock and turns into solid carbonate minerals, the same kinds of minerals found in limestone and marble. Once that happens, the carbon is no longer a gas, it's stone. You can think of it like a volcano in reverse. Volcanoes bring carbon up from deep inside the earth and release it into the atmosphere. Mineralization does the opposite. It pulls carbon out of circulation and locks it back in the crust. The chemistry behind this is not new. Earth has been doing this naturally for millions of years through a process called weathering. Rainwater reacts with rock. Carbon dioxide dissolves into that water, and over long periods of time, carbon ends up locked into minerals. The catch here is time. Naturally, this process takes thousands to tens of thousands to millions of years to make a noticeable dent in atmospheric carbon. And that's where new research comes in. In early 2025, researchers at Stanford University demonstrated a process inspired by cement making that dramatically speeds the chemistry up. Instead of waiting centuries, their method allows common rocks to react with carbon dioxide and form stable minerals in weeks to months. The same basic chemistry, just Very different timescales. The breakthrough wasn't a single exotic material or rare element. It was finding the right conditions, the temperature, the pressure, the surface exposure, to let the reactions happen quickly and efficiently using absorbent rock. That's a big deal. It means mineralization could, in principle, be done almost anywhere there's suitable rock, which is most of the planet. You wouldn't have to have a cap rock. No reliance on long-term containment. Once the carbon is mineralized, it's locked in place on geological timescales. From a risk perspective, that's about as permanent as carbon storage gets. But, and this is important, mineralization isn't a magic solution either. Turning gas into rock takes energy. Crushing and processing rock takes infrastructure. Moving carbon dioxide to mineralization sites takes planning and cost. And while the rocks themselves are abundant, scaling the process to billions of tons is an enormous challenge. There's also a trade-off. Mineralization is slower and more resource-intensive than simply injecting carbon dioxide underground, but it offers something underground storage can't guarantee: finality. Geological storage says, we'll keep it here safely. Mineralization says, there's no longer carbon dioxide anymore. That difference matters. So instead of thinking about the approaches as competitors, it helps to see them as tools designed for different jobs. Underground storage is about capacity and speed. Mineralization is about permanence. And together they point to something important. We're not short on ideas for dealing with carbon. We're short on approaches that work quickly, cheaply, cleanly, and massive at scale, all at the same time. Understanding those trade-offs is the key to having an honest conversation about carbon capture. Now, at some point in this conversation, someone's going to ask some very reasonable questions. Maybe they say, why are we spending all this money on fans and rocks? Wouldn't it just be easier to stop burning fossil fuels? Of course, the retort is, well, if we're building machines to pull carbon out of the air, does that mean we don't have to stop using coal, oil, and natural gas? And this is where the conversation usually gets off the rails. So let's try to slow it down. Instead of talking about climate, let's start talking about the cleanup. Imagine you're renovating an old house. You discover some mold behind the walls, decades of it. Some of the mold is still growing. Some of it is old damage that's already there. Someone might say, why bother cleaning up the old mold? Just stop the leak. That sounds reasonable, but stopping the leak doesn't make the mold disappear. The damage that's there has to be dealt with. The other side is, why bother fixing the leak? We've got great cleaning products. Well, that doesn't work either. If the leak keeps going, you're going to be cleaning forever. Climate change works the same way. We have ongoing emissions, the leak, and we have carbon already in the atmosphere, the damage that's built up. Carbon capture exists because stopping emissions alone doesn't instantly undo what's already there. The climate responds slowly. Heat sticks around. Carbon stays in circulation. But carbon capture only works if emissions are going down at the same time. Cleanup only works if you stop making a mess. This is what people mean when they talk about net zero. And net zero does not mean zero emissions. It means emissions get as low as possible, and whatever we truly can't eliminate gets balanced by removals. Things like aviation, shipping, cement, and steel production are extremely hard to make completely carbon-free. Even in a clean energy future, some emissions will likely remain. Carbon capture is meant to deal with the leftovers. It's not an excuse for business as usual. And that's why the order matters. We have to cut emissions first. We have to cut them hard, and we have to switch to cleaner energy where we can. Only then do carbon capture and storage make sense, not as a get-out-of-jail card, but as a mop after the leak is fixed. If someone tells you technology will fix it, you can agree partially. Technology helps, but only paired with restraint. And if someone says nature will fix it, you can agree as well, partially. Nature fixes slowly, but we're moving too fast. So the real answer isn't either or. It's both, for different reasons, on different timelines, for different limits. Once people see that, hopefully the argument can soften. Because most of us already understand the logic, we just don't apply it to the climate. Carbon capture is a bridge to the future, but it isn't the destination. It's a set of tools that can help us clean up the mess we've already made, while we do the hard work of building an energy system that doesn't add to it. It only works when it's paired with real reductions in greenhouse gas emissions. Cleanup without prevention just means running in place. What this research and these technologies really show us is there's no single solution. Climate change isn't a problem you fix through just one breakthrough. It's something you manage with honesty, limits, and long-term thinking. Understanding the trade-off matters. Knowing what the tools can do and what they can't matters even more. I'm Dr. Mack, and this has been The Climate Translation. If you have questions about the climate that you've been too afraid to ask, or you have a differing opinion, I want to hear from you. I can use your viewpoints in future episodes. You can reach me at theclimatetranslation@gmail.com. I'll see you next time.